Hello everyone, welcome to YourPedia Education. Today we are going to discuss the question which is asked in Airport Authority and that are from the topic of electrostatics. So we are going to discuss all the questions which are coming from the electrostatic topics in your past Airport Authority questions, Airport Authority exam. So basically most of the questions are coming from the electrostatics are basically depends on the electric field intensity. Let's start the first question. The two charge, that is the A charge and B charge is given to you that are located at. So first thing what we have to do to solve this question, we have to try to make a diagram for this one, right? The two charges are given to you and that are located at the location of -16 and 0, 0 and 12. So basically if I draw this one, this is your x-axis, this is your y-axis, right? So if I draw for the first charge, that is -0.4144 nanocoulomb charge, that is located as -16. -16 will be here, comma 0. That is your first charge A. Right, and another charge is located at a location of 0 and 12. It means that will be here. And we have to calculate the electric field intensity at a point -16 and 12 right here at this point P. So basically first thing what we have to do, if we calculate the electric field due to this A, charge A, that will be in the direction of this one. Right, because this is a negative charge and in negative charge the electric field is always coming towards that one, and if I go for this due to this B charge, this is a positive charge, you can see here, so electric field will go in this direction. So what will be the angle between these two electric field? If I write it, this is the electric field EA and this is the electric field EB, the angle between these two electric field is 90 degree. If we calculate the resultant electric field, the total electric field at this point P, that will be under root of EA square plus EB square, because the angle between these two vectors, we will study this thing in mathematics, that whenever two vectors are perpendicular to each other and you are calculating it their resultant, right? If I calculate their resultant, then I have to connect this one like this, right? And this is called resultant electric field, right? Resultant vector, right? So basically this is your resultant vector. So resultant vector is always what? E under root of EA square plus EB square. Got it? So this is the formula which we are going to use. Now another thing, the electric field due to a point charge, that will be given by you, that is 1 upon 4 pi epsilon naught Q upon R square. This is the magnitude of electric field. If you are calculating due to this A charge, you have to put the value of QA and the distance between this point and this point. Distance between this point and this point, what you are seeing, that distance is 12 centimeter. Right, we are going to use that one, right? So if I calculate that distance, that is 12 centimeter. Either you can use this formula, or either if you draw this figure, then you can easily check that what is the distance between this point and this A point. So directly we got the distance between these 2 points, R we got, and charge we have this 1 upon 4 pi epsilon naught is how much? That will be 9 into 10 raised to power 9. So if I plug in all these values, I will got the value of the electric field EA, that will be 90. So basically due to this A charge, the electric field is going down and having a magnitude of 90, right? You can check it here. Again, if I want to calculate the electric field at this P point due to this second charge B, that will be going look like this one, right? And whenever you calculate the electric field, this time the distance from this point, between this point and this one, that will be 16. So distance is 16, magnitude of charge is already given, right? If you put that one and you calculate the electric field E2, right? If you calculate the electric field E2, so E2 or EB, that will be 9 into 10 raised to power 9. I am calculating only magnitude and then I plug in the values here and I will get the final answer. So that is going to be 0.2 256, nano means 10 raised to power minus 9, divided by r is the distance 16. 16 means if I convert it into meter, 0.16 whole square, and you solve this, this will cancel this thing, right, and you will got that is again 90. Yeah, so one is minus 90, other one is 90. When you calculate the magnitude of these two, that will be 90 root 2. So 90 into 1.414, like that. If you multiply that, you will get that will be 127, right? That is the answer, 127 nanocoulomb. So hopefully you understand the concept behind this question. Try to draw the figure. Whenever you find any question from the electric field, just draw that figure. When you draw that figure, right, when you draw that figure, you easily figure out that what should I apply, what is the distance between the point and the charge, right, everything, and that will be easy to solve for you. Now in a dielectric material, the polarization P and the displacement vector D and the electric field vector E are related with each other. So always remember that D is equals to P plus epsilon naught times E. That is the most important relation, right? See, basically if I am talking about airport authority, the most of the questions are directly formula based, because they are asking the physics from up to 12th level. So they will ask you definitely these formula based questions, right? And you no need to go in that much depth. What is that? What is this? What is that? Right? No need to go in that much depth. I will teach you each and everything in detail whenever we go to the classes. But here D is called as displacement, right? Displacement vector, generally we denote it as electric flux density, right? E is represent electric field intensity, P is represents the polarization vector. So that is the relation. If I calculate the value of P, the P is going to be D minus epsilon naught E. So what will be the answer? The answer will be, that is not the D will be the answer for this question, D minus epsilon naught E. So that is the answer for this question. Okay, next, electric flux passing through the surface A and electric field vector E is given by, see, whenever you are calculating the electric flux, right, whenever you are calculating the electric flux passing through any surface, so electric flux phi generally denoted by E dot area, E dot A, right, E is given to you, that is 2 I cap plus 3 j cap minus 4 k cap. When you do the dot product of this one with 8 j cap, so only this factor will multiply with each other, rest of the thing becomes 0, so that is become 8 into 3, that is equals to 24. So the answer will be 24 volt meter, right? Next question. A closely wound solenoid 80 centimeter long has 5 layers of winding with 4 00 turn in each. Each winding has that much turns and there are 5 layers of that one, right? The diameter of the solenoid is 1.8 centimeter. The current carried out by the solenoid is 8 ampere. A magnitude of magnetic field intensity inside the solenoid. So magnitude of magnetic field intensity B is equals to mu naught Ni over A. Oh, sorry, not A, L. Right. So basically N is the number of turns, because there are 5 layers and each layer having 400 turns. So total turn is 5 into 400, that is 2000. So there are 2000 turns. So mu naught value is how much? 4 pi into 10 raised to power minus 7. N is 2000 and I is 8 ampere divided by L. So the L will be yeah, the solenoidal wound 80 centimeter long. Yeah, length is 80 centimeter. So there is no use for this 1.8 centimeter. So don't worry about these things. Sometimes they will give you extra information so that you will confused. Right, that is become 2.5 into 10 raised to power minus 2 Tesla. That is your magnetic field, right? Next question. A parallel plate capacitor has a capacitance of C if its distance between the plate is reduced by half, right? So if I talk about the capacitance of a parallel plate capacitor, that is epsilon naught A upon D. That is the parallel plate capacitance, right? Whenever you do reduce the half and the space between the plate is filled with the medium having the electric constant 6, the new capacitance will be see, basically this is the first capacitance. Let us take this is C1, not C1, that is C, right? This is C. The first capacitance is C. The new capacitance, let us take, that will be C dash. When you fill with the having a dielectric constant 6, right? Dielectric constant 6 means 6 epsilon naught A. Areas remain same, and we will do the separation between the plates is half. So that means it is become D by 2. So what is happened? That will become 12 times epsilon naught A upon D. So this value is again going to be C. So C dash is going to be what? 12 times C. So what will be the answer? Answer will be the B. So that is the question. Now what is happening? This is most difficult question, you can say, till now, which is coming in airport authority, right, from the electrostatics. Rest of the questions are easy, right? This is the most difficult question. So basically what is happening here, a very small sphere of a 60 gram, this sphere having a weight of 60 gram and charge is Q, right? The charge is paired on the sphere is Q, held at a height of 7 meter vertically above the center of the fixed conducting sphere of radius. Okay, that is asking about this one, a small sphere, right? He is telling you that this is your small sphere, this is your small sphere here, right? He is talking about this one that is having a 60 gram of weight, right, mass, and it is having a plus Q charge, and it is adjusted at a height of 7 meter vertically above the center of a fixed conducting sphere of radius 1 meter, carrying equal amount of Q charge. When released, it will fall until it will replicate back just before come in contact. See, basically whenever it fall, so what is happening, the gravitational force will be applied in downward direction and electrostatic force will be applied in upward direction. At one position, when your gravitational force is equals to the electrostatic force, then it will be come into picture. When it goes little bit down, then the electric force will increase and that will replicate this one, its speed going decrease, and at some position it will start going back. So that what he is asking, that when it release, it fall until it replicate back just before it come into contact with the sphere as shown in the figure. So we have to calculate the charge Q. So what we have to do here, so basically first thing what we have to do, we have to calculate the potential energy stored in the system initially. So the potential energy is what? 1 upon 4 pi epsilon naught Q1 Q2 upon R. That is the formula. See, basically the distance between these two charges is 7 centimeter or 7 meter, right? And gravitational potential energy for the sphere, that will be 1 mg, right? And when we calculate the total potential energy, that will be the sum of these two, and we will equate that one with the final potential energy. When this mass is going down, before it come to contact, right, the potential energy will be 1 upon 4 pi, because when it will come into contact, the distance between the center is become 1, so R is become 1. So that is the potential energy, right? So we will equate that and we will calculate the Q upon 4 pi epsilon naught, that will become 7 mg, right, like that. So when you solve from this equation, we will calculate the value of Q, that is going to be 21.6 microcoulomb. So this is the question where we calculate first potential energy at this position, and second when it will again going into be rest, right? So that means when it will be rest, the potential energy again come into picture. That means when start falling here, the kinetic energy is 0. When it reaches to the position when it will start replicate or start going backward direction, at that position its kinetic energy is again 0, because velocity is 0 at that position. So we calculate the two potential energy and we equate them, because energy is always conserved there, and we calculate the value of Q from there. right? So next thing is what? Which of the following material behave as a dielectric? Which of the following material will behave like a dielectric? See, basically dielectric are the material which are non-conducting material, you can say. So the good dielectric materials are what? Air, water, diamond, ceramic, plastic, mica and glass. These are the example of good dielectric material. So in the inside this one, tungsten is a material, metal, copper is metal, germanium is semiconductor and mica is a dielectric material. Which of the following material exhibit the piezoelectric effect? The piezoelectric effect is applicable to quartz crystal, right? Whenever you apply a pressure on the quartz crystal, it will generate a potential across its terminal, right? That is called as piezoelectric effect, right? So basically copper is a metal, aluminum is a metal, iron is a metal, the quartz material is a piezoelectric materials. These are the piezoelectric material: link, PZT, lead, zinchronate, titanate, barium titanate, lithium nitrate, crystals, ceramics, like that, right? So quartz is a piezoelectric material. Next is the electric field between two plates of a parallel plate capacitor is given by this. What is the magnitude of displacement current between that? So basically first thing what we have to do, if I am talking about electric field is given to you, so basically the displacement current density ID, that is the derivative of del D over del T, and D is Zernal medium, that is epsilon naught E. So what we can say, the displacement current density multiplied by area is also there. So current density JD, generally we denote this by JD, so that is epsilon naught del E over del T. So we have to take a derivative with respect to the time. So when you take the derivative of electric field with respect to time, you will go to this one, right? Del E over del T, flux density D E, yeah, and you will calculate that value, that is your flux density, right? Current density. When you multiply that with the area, that is become current. So basically the first relation is JD. JD is the current displacement current density, that will be epsilon naught del E over del T. This is your current density. If you want the current, then you have to do one thing, you have to calculate ID, that will be JD times A. So first we calculate JD, or either you can do one thing, directly calculate the E times A first, and then you have to take the derivative and you will get the same answer, right? So that is the process. So just the calculation you can do that one, right? I already did that calculation here, you can check that, right? The main concept is though that current density JD, displacement current density JD, that will be epsilon naught del E over del T, right? From the current density, if you try to go to the current, then you have to multiply that one with A, area. So it is going to be 1.77 10 raised to power minus 8. Again, two parallel plate capacitor having an equal and opposite charge of magnitude, space between the plate is filled with the dielectric. If the electric field in the dielectric is this one, what is the magnitude of charge induced on each dielectric plate? So charge induced on each dielectric plate is given by this formula. Q dash is equals to 1 minus K into Q, right? Everything is given to you in the question. You can calculate the value of K from this one, right? And when you got the K, you can put that value there and you will got the Q dash, right? Everything is given to you, just put it here and you will get the value of K, right? Next question. Assume a parallel plate capacitor which is maintained at a potential of 100 volt if partition distance between the plate of the capacitor and area of the area of the plate is given to you, then compute the displacement current density. Again, displacement current for the time in microsecond. I think something is missing here. The time will be time is given to you, right? At this particular time you have to calculate that one, right? So the first thing what we have to do, we have to calculate the electric field intensity. See, inside the capacitor electric field intensity is over, what is the electric field intensity? That is del V over del T, right? So del V over wait. Electric field intensity, we have to calculate not electric field, that is electric field intensity, that is V over D. Voltage upon distance, that will be V. Voltage, how much voltage is given to you? Let me check it. V over D. Yeah, potential is given to you, that is 100. So 100 over D. D is the distance between the plate, that is 5 mm. 10 raised to power minus 3. When you solve it, you can check it here. The electric field intensity is given by this one. Again, electric displacement current density, area times, I am making this area times, then we have to multiply epsilon naught del E over del T. You can use this formula, right? And everything is given to you. He is asking for the time, right? Let me check it. Yeah, so that will be the formula, and we will put in the above equation the T value. I think T value is missing in this question, right? That will be written here. I didn't get this, so that value is written here, and we will put that here, and we will get the final answer from this equation, right? Electric field intensity at the center of a uniform charge distribution hemisphere. Whenever you have a hemisphere like which charge is distributed uniformly, and we have to calculate the electric field intensity at the center, right? So what we can do, we can choose a small length ds and calculate the electric field due to that length ds at the center. Then we will integrate that ds with respect to this theta. Theta will vary from what? 0 to minus 90 to 90, right? You can say 0 to 90 or like that. So every value I will put it here. This is the derivation, you can check it. This is the derivation, and the finally we will got the value 0 to pi by 2, and we will do it twice, right? That is the things. Okay, next question. Let the electric field apart from electromagnetic wave. Yeah, this is the electromagnetic wave, and electric field of this electromagnetic wave is given. Compute the value of wavelength. Okay, so basically the electric field E is given by E naught. That is the question from EM wave. I think it come here, then I have to discuss it here. Omega t minus beta I cap. That is the formula, right? Omega is given to you, right? Beta is given to you. Okay, beta z omega t, that's the question is not completely written. Omega t minus beta z, like that, right? So we have to calculate omega. Omega is 2.4 into 10 raised to power, that is 2 pi f, and it is given to you 2.4 into 10 raised to power 8 is equals to 2 pi and f. So we have to calculate the f value from this one. So when you calculate the f value, that is 1.2 into 10 raised to power 8 divided by pi. So basically if you treat this pi as a 3 and that is 12, so it is around 3, means just below 3. So this value is going to be 3.82 into 10 raised to power 7. One value we got it here, right? And what is calculating? The wavelength. See, basically we will travel in the free space, so c is equals to f into lambda. So the wavelength is going to be 3 into 10 raised to power 8 divided by 3.82 into 10 raised to power 7. So that is 30 into 10 raised to power 7 divided by 3.82 into 10 raised to power 7. When you calculate it, you will get the value of the wavelength, right? Wavelength is going to be, either you can directly calculate that one. Yeah, this is the complete equation that is misprinted there, right? That is the complete equation, 2.3 cos of 1.2 y and 2.4 into 10 raised to power 8. So this is your beta, this is your beta. So beta, or you can say the k wave number, sometimes it is written as beta or wave number, that is 2 pi by lambda, right? And lambda will be the value, and we will use we have to calculate, so we can use that lambda is equals to 2 pi by beta. Beta is 1.2, so we will got it here 5.23, right? Omega f we already calculated, and E upon B naught is equals to C. From here you can calculate the value of B naught, right? Next, a copper wire of a uniform area of a cross section right? A copper wire of a uniform area of cross section 3.4 into 10 raised to power 5 meter square carries a current of this one. The magnitude of electric field applied is. See, basically whenever we are calculating, current is given to you, cross sectional area is given to you, we have to calculate the magnitude of electric field, right? Copper resistivity. So first what we have to do, we have to calculate the copper wire of uniform cross section carries a current of this, that the magnitude of electric field is applied by this one. Okay, so basically first we have to calculate the resistance, that is rho L by A, right? Let us take that is for unit length. So R is equals to rho is given to you 1.7 into 10 raised to power minus 8, L is 1, area is given to you how much? So when you use this value, you will calculate the resistance, right? You can calculate the resistance, that will be 1.7 divided by this, that will be 2. So it is going to be 10 raised to power minus 3 divided by 2, that is your resistance. And from this resistance we can calculate the voltage. Voltage is equals to V is equals to IR. I is how much? 4 times 10 raised to power minus 3 divided by 2, so that is become 2 into 10 raised to power minus 3, that is the voltage. And electric field is denoted by what? Electric field is denoted by V over D. D is 1, so the electric field is going to be how much? 2 into D is 1, right? Voltage we already calculated, 2 into 10 raised to power minus 3, answer is D. A vacuum 2-point charge of the magnitude this are separated by the resistance of 6 mm along the x-axis. Halfway of the at the halfway point of the separation of distance, the electric field will be. See, basically you have two charges, right? One have the magnitude 1.8, another have the magnitude of minus 1.8. It means we have two charges here. One is here, another one is here. That is having 1.8 nanocoulomb, that is having minus 1.8 nanocoulomb. And at the center, if I calculate the electric field due to this charge, electric field is in this direction, and this is negative charge, the electric field will come in this direction. So basically distance between these 2 points halfway, the vacuum 2 points are separated by 6 mm. Yeah, this distance is 3 mm here and this distance is 3 mm here. The magnitude of electric field for both the charges will remain same because only the direction will be changed, right? So the formula for electric field is what? 1 upon 4 pi epsilon naught q upon r square k. 1 upon 4 pi epsilon naught is value is 9 into 10 raised to power 9, and q, the charge of one charge 1.5 in 1.8 into 10 raised to power minus 9, and you put it all the values and you calculate the electric field, that is 1.8 into 10 raised to power minus 6, and you can just do it multiply by 2, that is 3.6, because both the charges having distance same, magnitude of charge same, but what we are seeing that electric field due to both the charges in the same direction, so that will be added and that will be just twice, that is become 3.6 into 10 raised to power 6. Yeah, next question, which of the following are correct? Okay, Gauss law applicable any closed surface regarding the shape or size of the surface. See, basically whenever we talk about the Gauss law, right, Gauss law says that the charge enclosed by any closed surface. He is not talking about that the shape of the size of the surface is what. It just says whenever you have a closed surface, the electric flux density out of that surface is equals to the charge enclosed by that surface. So that is not depend on the you can say the size or shape of the surface, right? We cannot distinguish between positive and negative flux described on the direction of the electric flux line. See, basically we can distinguish between positive and negative flux. Positive flux which is coming out of the surface, negative flux which is going down inside the surface, that is called as negative flux. Net electric flux leaving a surface will always be 0 if there is a bound inside, the charge bound inside of it. See, whenever any surface having charge inside that one, until or unless the net charge will be 0, the electric flux electric flux will never going to be 0. So only the statement 1 is correct, right? Next, yeah, already discussed this. The surface charge density of a tiny sphere cell placed in an air medium is 68.54 coulomb per meter square. The intensity of electric flux is measured 12 mm outside the cell. From the center of the cell is that much. The tiny spherical cell has a radius of, okay. So basically when we talk about the electric field intensity outside that tiny sphere, yeah, we will derive that a relation in class, that is sigma upon epsilon naught r square over x square. That is the formula for electric field intensity outside that spherical cell, right? So whenever all the values are given to you, sigma is given to you, sigma is representing charge density, just plug in here. E is equals to what? That is 68.54. Radius we have to calculate, so r square as it is. X is the distance, that is 12 mm. 12 mm means when you do 12 into 10 raised to power minus 3 square, and electric field is already given to you, that is 5.625 into 10 raised to power 12. So when you solve it completely, you will get the value of r, that is 9 mm. That is the process how you can solve this. So remember, this is the formula for electric field intensity outside is spherical side. Okay, suppose a uniform electric field is given to you, then the flux of this field passing through a sphere of 12 centimeter on the side whose plane is parallel to the xz plane. Okay, electric field is given to you. Okay, basically what is happening here, electric field is going into, this is, let us take, this is your xy plane, right? X1 y. Electric field is going up like this, in this direction, right? And we have, this is your x-axis and the outside is your z-axis like this. Here we have a square plate, right? We have a square plate 20 centimeter side. So area of this square is 20 into 20. Basically electric field is passing through this point like this, right? Upward direction. So if I talk about this area is also having the direction in y cap, right? So that means if we calculate the net flux passing through that one, that will be E times the area of this one, means 20 into 20 into 10 raised to power minus 4. So 4 into 10 raised to power minus plus 4 multiplied by 20 into 20 into 10 raised to power minus 4. This will cancel out. So 20 into 20 is 400 into 4, that will be 1600. That is the. So basically if electric field is going in this direction, that means it is passing through, this complete electric field will passing through this one. So if you are calculating the flux, that is, remember, E dot area, right? Here the dot product, if they will make an angle, then you have to take a cos theta there, right? Accordingly you can change your answer. Next, a sphere of side 5 centimeter is placed inside an electric field in such that the normal vector of for the seat is this one, the electric field. Yeah, this is the same question. You have to calculate the angle between this one and this is the unit normal vector. You have to calculate the angle between this electric field and that one. Or either you can do one thing, you can do A dot A. You can do directly dot product between those two, or either you can calculate the angle. So phi is equals to EA cos theta, right? Angle can be calculated, that will be tan inverse of imaginary part upon real part, that is 30 degree. You can directly use that one and you will get the value, right? So I already discussed this thing with you. Whenever you are having a normal incidence, then you can directly do that. If you are having an incident at an angle, then you have to calculate the angle between the normal and that you can say the electric field, right? If you calculate that angle, you can use this formula, r is equals to this given and theta is equals to imaginary y upon x, like that, right? That will be 30 degree. A charge q1 of 3 microcoulomb is placed at a distance, another charge 9 microcoulomb is placed at a distance of this one. Let ij be the unit vector in xy direction. The force on q2 and q1 are. See, basically whenever you are calculating the force, the formula for the force F is equals to 1 upon 4 pi epsilon naught q1 q2 upon r square, right? So basically the one thing is that, right, we are having the force, yeah, we are trying to calculate the force extract by q2 in q1. So first thing we have to draw the figure, right? This is the formula for the force. So first we have to draw the figure, right? The figure is says that q1 charge is 3 microcoulomb at placed at 36, yeah, q1 is here, and q2 charge minus 27 here. So basically if you are calculating the force extract by q2 on q1, this is negative charge or positive charge, 9 nano microcoulomb, and this is also 3 microcoulomb. So if we talk about the force, that will be force of repulsion like this. It is having two component, that is x component and y component. So remember that is I and j. So basically in this type of question sometime you can directly solve that one. See, I make a figure like this, the electric field is, sorry, force is going in this direction, that is having I component and plus j component. So basically only one question have this one. So these are the tricky question. If you got the trick, no need to calculate everything, because in the option what I am seeing that I is negative here, j is negative, I is negative, j is positive, I is positive, j is negative. Only one options having that, which is having, because our force is going in plus j direction and plus I direction, right? So that means we can eliminate other options, the answer will be D. Otherwise you can follow this complete process what we did here, you can calculate the exact value. But in MCQ types you have to check that how we can sort our times to solve a question, right? How you can go from the options, right, like that. Okay, A is a charge, B is a charge located at a distance. Yeah, the magnitude of electric field at a point of this one. This is the similar question. If you check, this is the same type of question which we did first, right? That will be easy for us to calculate, right? How we can do that? Again the same thing, you have to make a figure first. I have to make a figure first, right? First charge is at what, 3, and that is for 0, 4 here. We have two charges and we have to calculate the electric field here. So first electric field in this direction, second electric field in this direction. Calculate these two electric field. When you are calculating the first electric field, you can use this distance, right? This distance for this Q, let us take QB charge, right? QA. So when you calculate due to QB, you use this distance. When you calculate QA, then use this distance. You can directly calculate the electric field EA and EB. Then final resultant electric field, because they are making a 90-degree angle. So resultant electric field will be under root of EA square plus EB square whenever they are making a 90-degree angle, right? Suppose every second 10 raised to power 16 electrons come out from a body, right? Okay, the body and move to the another body, right? That much electron are coming from the first body and that are going to the another body. Then the time required to get a total charge of, see, basically whenever we calculate the charge is Q is equals to NE. The total charge is 3.2, that will be equals to N number of electrons times charge on one electron, that will be 1.6 into 10 raised to power minus 19. So generally when you calculated here 2, so N is equals to 2 into 10 raised to power 19. So to get a charge of 3.2 coulombs, that much amount of electron should be passes from first body to second body. So it means if we are calculating time, how much time it will take to go 2 into 10 raised to power 19 electron from first body to the second body. So you have to do 2 raised to power 19 divided by 10 raised to power 16 and you will get the answer, that much amount of second. So 2000 seconds it will take to go 1.3 coulomb, 3.2 coulomb charge from first body to the second body. Consider the magnitude of electric field at a point at a distance r due to a infinitely long straight wire charged with a uniform charge density lambda. than the given V. Okay, so basically when we are calculating the electric field due to a line charge, that will be E is equals to lambda upon 2 pi epsilon naught R. That will be the formula for the electric field. So basically it will be inversely proportional to the R. Electric flux through a rectangle is, basically this is again the not complete question, some information is missing. Electric field is given to you and area is given to you, right? Normal vector is given to you, you have to calculate the electric field. That will be like this, right? Okay, two charges A and B are given located at a distance. Yeah, this is again the same question which we already did, right? That is 127. Next, suppose that three equal charges each charge equals to plus q are placed at a vertices of an equilateral triangle of side 1 centimeter. The force exerted on a charge q placed at the centroid of the triangle. See, whenever you make a figure like this, this is the figure for equilateral triangle, and you are calculating the force on the center, right? So the first AD, we calculate the distance AD. This distance AD is AB cos theta, L cos theta, right? L cos theta, theta is 30 degree because it's equilateral triangle, each side having an angle of 60 degree, so center angle having 30 degree. We calculate root 3 by 2, and the distance AO, we calculate AO distance, that will be 2 by 3 times AD, right? You calculated this distance. The force on Q due to Q1, so force on Q, that is the charge here due to Q1, like that F1, F2 and F3, you calculated them and you add them, that will become 0. Why it is become 0? Whenever you calculate the force due to this one, remember this is the equilateral triangle, so force due to this one is down, due to this one in this direction. So when you take a component of this one, that will come here, this component is here. When you take a component of this one, that will go here and in this direction. So these two components will cancel each other, and this component will be cancelled by these two components. So net force will be 0 there, right? Compute the Cartesian component of electric field at a point of the potential at any point. Potential is given to you, you have to calculate the electric field component. So electric field is what? Remember, what is the relation between electric field? That is del V over del X I cap, del V over del Y J cap. You have to take the derivative with respect to X. When we take the derivative with respect to X, we will got first value is Y square, and when you take the derivative with respect to X, that is become 12 X square. Yeah, minus is also there, minus gradient of V, so minus is also there, that is I cap, and when you take the derivative with respect to Y, that is only having with respect to 2, yeah, minus is already there, 2yx j cap, right? So that will be the answer. When you minus and multiply, the minus will inside, that is become 12x square minus y square, that is I cap, and the other one is become 2xy. I already covered this minus here, right? 2xy with the minus. So these are the two component, x component and y component, right? Next, given an isolated conducting sphere cell of radius 30 centimeter, some positive charge is given to it so that the resultant electric field has a maximum intensity of 1.8 in 10 raised to power Newton per meter is Newton per meter. Then the same amount of negative charge given to the isolate the conducting space of 60 centimeter. Now the first cell is placed inside the second cell. Both are concentric, are given in the figure. Find the electrostatic energy stored in the system. So what we did first, for the smaller sphere electric field is given to you maximum, then we will calculate the Q from there, right? Now the capacitance, and from the capacitance we can calculate the energy of the system. Whenever you put two sphere like this, they will behave like capacitor, and you can calculate the energy stored in the capacitor, that is Q square upon 2C, right? Now next, 2-point charge of 2.6 into 10 raised to power minus 19 coulomb and minus 2.6 into 10 raised to power 19 coulomb are separated by each other with the distance of this one, the dipole is situated in a uniform electric field is equals to this. Yeah, so if you are calculated, find the work done is always equals to the final potential energy minus initial potential energy, and potential energy is given by minus PE cos theta. P is represented by the dipole moment, and we can calculate it theta 1 minus theta 2 and just plug in 0 to 180 degree and plug in the values, you will get the answer. When it 3 microcoulomb of charge is carried by a point, and okay, you have carried it from A point to B point. Let us take here, this is A point, this is B point. If we have carried out a 3 microcoulomb charge from A to B, the amount of work done by the electric field is that much. Determine the potential. See, the potential is equals to always the work done per unit charge. Just plug in the value. Work done is given to you, charge is given to you, right, and you will directly calculate the potential, change in potential difference, or you can say potential difference, right. A non-conducting sphere of radius center at origin coordinate system as shown in the figure 2. It is two spherical cavity of radius r1 whose center is at that one and that one respectively. The solid material of sphere has a uniform positive charge density. Compute the electric potential. This is the system and you have to calculate the potential. So you can directly use Q1 Q2 and you can calculate the electrostatic potential Vp, V sphere and minus 2 cavity, like that. This is also a difficult question. If you are going for this exam, airport authority, whenever you see this type of question, you can leave them. Okay, that is the advice to you, because it will take lots of time to solve and you have a limited time, right. You have to decide that which question I have to choose to solve or which I have to leave. So this is the question which you should leave. No need to invest your time, because it will take lots of effort and lots of time, for lots of calculations are there, right. So I suggest you that you have to leave this question. No need to solve this type of big questions. It will consume your time, right. This is the question. I found this question is difficult, and the first which I told you that this is also a difficult question. These two questions cannot be done in 2 or 3 minutes. It will take around 5 to 10 minutes, and that will take your rest of the time from other questions. So whenever you see these type of questions, just leave them, right. That is the key of success. If you invest your time, let us take you invest your 10 minutes and you solve this question, right, at the end it will leaves you that it will cost you, you can say it will cost you around 2 to 3 marks, right. So that is the suggestion from my side. Whenever you solve the paper like airport authority, where we have a fixed time of 120 minute and each question has 1 minute, and you find that any question is taking around 4 to 5, 6 to 7 minutes, it means it will take the time of the other questions also. So just leave that question. It will not affect your selection, right, because that is also difficult for each one. If you leave this and you can do easy question, 2 or 3 questions, right, that will be beneficial for you. So hopefully this part I already covered with you, right, and it will help you in your exam. That is from electrostatics. The next I will cover from magnetostatics. Hopefully this will help you. Thank you.